So hi everyone, welcome to the end of the second day of JavaOne, and thanks for coming. I'm going to be talking about a subject I've been kind of developing, working on for a while, both for talks and conferences, but also in real-world product. I call this Cloud Native JVMs, and I emphasize that I call this Cloud Native JVMs. I've managed to get some other people to call it that too, but I have a definition here, so we'll get to that. The name is not entirely snarky. This is parts 1 and part 2 of a longer path towards an entire view of what Cloud Native JVMs are. These are not the only 2 parts, but there are 2 parts to talk about, and together they actually give us an interesting picture that is very useful for fleet-wide profiling and optimization of modern deployments. I'm Tene, by the way, for those of you who haven't read the thing. And if you don't know me already, you could probably Google and find a bunch of stuff. I've been to many JavaOnes. I've spoken about a lot of things, garbage collection and optimizations, and how not to measure latency. And this is just another subject that I've started diving into for the last several years. I want to start with what are Cloud Native JVMs, and to take kind of a step back from even the JVM part, let's think of it as Cloud Native runtimes. And what do I mean by that? Runtimes are prevalent. They're everywhere in what we build and run, and we have a lot of languages out there. Most of them today run on some sort of a managed language runtime. If we look at some sample of the common languages we write code in today, or code that is out there, gets written in, here's a slapping of a bunch of them. Everything above the line is running in a managed language runtime. The things below the line don't, or don't have to, and typically don't. The Rust people will vehemently say we don't have a runtime, and most C and C++ don't. But everything above the line absolutely has a managed language runtime, and these are the managed language runtimes those languages run on. So in every one of those cases, you're not running directly on a machine or directly on the operating system. There's something else there that's doing stuff. Now, that stuff could be thread management, it could be garbage collection, it could be communication, it could be just abstraction of the hardware, it could be adapting to a CPU or an operating system. But we commonly write to these things today to the point where probably well over 90% of the code being written is running on these things from now into the foreseeable future. This is not to say that people don't code in Rust and C++ and even in C. But the amount of code we produce is tremendously focused on this level. Now, why do people do this? We can theorize, and there are many possible reasons in productivity and agility, and that's who we can hire. But the reality is it doesn't matter why. This is just how the world is. And we don't need to argue this. It's a fact. I'm not here to evangelize managed language runtimes being a good thing. It's just what we do, right? Within that world, JVMs are one of the managed runtimes that are massively used, one of the better performing ones, one of the longer track ones, one of the stable ones. We're all here at JavaOne, so we probably have an affinity to it. So when we look at the Cloud Native managed runtimes that I'm talking about, I'm looking specifically at JVMs and what we can do about them, or what does it mean to be a Cloud Native JVM. So what do I mean by Cloud Native as opposed to not Cloud Native? We need to kind of contrast to understand what we're talking about. And to that, we could look at historically and even currently some of the common qualities of JVMs and managed runtimes in general. To start with, JVMs, as we're used to seeing them, are isolated. They stand by themselves. They don't connect or know about any other JVM. They might even be talking to another JVM, but they don't know it's a JVM. They just know it as an external thing that's some other application. They have no memory of what happened before they started. There's no past to a JVM. There's no I've done this before. I don't need to do it again. We start, we load the code, we run it, we make it go fast, we make it happy, we finish, right? The JVM is entirely self-reliant. Everything it does on its own, and that means it can only use the local resources. It can only use whatever functionality the local machine or container it's in can do. And it has to deal with the trade-offs of resources, wall clock time, cost, and optimization, for example. It doesn't have a magic cloud. It doesn't assume one exists. So that means it has limited compute power. It has limited data storage. Has limited functionality to whatever you could do on the local OS. It has limited ability to run some analytics for fun. And it has limited knowledge about anything outside of its own experience, its own short, ephemeral experience. But this world that we built JVMs into was the 1990s. Runtimes in general started in the 80s, 90s. In that world where we were building it for a PC or a server that didn't necessarily have a good, reliable network connection and the internet was just starting up, this made a lot of sense. We couldn't assume that we sit in some magic cloud. But today we can assume otherwise. If we are building to run in the cloud, we have to assume the cloud exists. And that means we can actually rely on it for some things. For example, we can assume that the network exists and it's reliable. The network isn't really reliable, but if it's not reliable, this thing has bigger problems, right? We can assume that we can leverage all kinds of other things, like external resources that we think exist, and functionality and experience that is accumulated outside of our own instance. We can leverage and we can actually contribute to some bigger whole so that this whole thing together would work better. We can assume an access to an actual magic cloud with all these infinite capacities that are out there today that didn't exist when we thought of what a runtime and a JVM was 25, 30 some years ago. So I'm going to define what I consider to be a Cloud Native JVM with the minimum requirements for one. And I try to go as minimal as I could go, because I didn't want to say it has to do this specific thing. Here are the three things you need to be a Cloud Native JVM. First of all, you need to be a JVM. Okay. This might not seem obvious to some people, right? You can't do sort of what a JVM does. You can't do half of what a JVM does. You can't say stuff like, well, this will work as long as you don't load classes. Or this will work as long as you don't do reflection. Or this will work as long as you don't use sunMISC unsafe. It needs to be a JVM from a specification point of view, but also from the simple testing point of view that everything that runs on a JVM today in Maven Central needs to also run on this. If it fails at that, it's not a Cloud Native JVM, it's something else. Okay. In addition, it needs to outsource something, some key functionality that normally you do inside on your own, relying on yourself, to that cloud, the cloud that's around you. And the third one is that you need to deliver something into that cloud, something of value that others can use. For example, other JVMs, not you, could use what you delivered. If you tick all three of these boxes, you're doing something that is a Cloud Native JVM. Now, there are many things you could do that would fit into these three categories, and I'm going to talk about two of them, part one and part two. Each individually does this, and there are many other potential things you could do. So we're going to talk about part one. Part one in my book is Cloud Native Compilation. Let's talk about what that means. Here are the insides of a JVM, roughly speaking. It does a lot of things. It's got JDKs and classes, and it's got a runtime, it's got class loading and garbage collecting and lots of other things, but we're going to focus on this thing here. That's the JIT compiler. JIT compilers basically do a simple but large thing. They do the heavy lifting of translating bytecode to optimized machine code. It's a contained thing to do, but it's a very expensive, heavy thing to do at the same time. Now, how does the JIT compiler do that in a modern day runtime? The JIT compiler doesn't know much about what's going on, and the rest of the JVM doesn't know much about how to optimize anything. So there's a conversation that happens between these two parts, where the JVM kind of starts with, here's some code I would like to be better. Now, the reasons for doing it are up to the JVM. The JVM might decide that it's seen this code run 1,000 times. Maybe it could be better, maybe 10,000 times, and maybe it could. Or maybe some events happened that made other code not valid. We should do this again and now do this. Why the JVM asked to make the code better doesn't matter. It starts the conversation. It says, hey, JIT compiler, here's a method, please optimize it. But that's as far as the JVM actually knows what to do. Everything else comes as a result of the JIT compiler interrogating the JVM and asking it a lot of questions. So you give me this method. That's nice. This method seems to call that method. Could you give me that method too, please? And I see that this is using a static final. What's the value for that? And there's an if here. What's been your experience about how people use this if? How many times do you go right and left? Did they ever go left? Here's a type, here's profiles, examples, and facts and constants and things about the class hierarchy. The JIT interrogates the JVM, and it asks it a lot of annoying questions. And at the end of a very long conversation, it says, I think I'm done. Here's something that I think is the good solution for this problem. And you can try and run that. So at the end of this conversation, the JVM basically gets an outcome, an object file. Go put this in and run it. And it's going to replace whatever it currently uses for running that method with this thing. All this is happening in the background while the code is actually running something slower or other. And all this is happening currently completely inside a JVM. A JIT compiler is part of a JVM, and it's talking to the rest of it this way. And there's a lot we can do here. Now, when we look at JIT compilers, why do they exist? It's because we want to run fast. We want speed. And if we say we want speed, you often have to ask, so what do you mean by that? We kind of understand speed is doesn't take a long time to complete, but how does speed behave? We'd like it to behave like this. There should be some number. It's 17, and it's always 17, but it isn't. In the Java world, it kind of looks like this. This is the shape of speed over time for applications. And we have names for the parts of the speed. There's startup, which is how long until I get a heartbeat. There's eventual speed, which is once I finish doing everything and optimizing, that's how fast I am. There's this warm-up curve that is between the two until I get fast. And there are all these other hiccups and stalls and whatever you want to call those down things that we're not going to talk about here, like GC pauses, right? But fundamentally, we evolve into speed. The way we evolve into speed is by having every method that is actually executing go through an independent evolution path. And that evolution path looks something like this. The x-axis here is time. The y-axis is a % of code of a certain type. The yellow is interpreted code. Green is slightly optimized, but mostly profiling code. And then the blue is what we really want. Fast code optimized to run the way we want it for this CPU with what we've actually experienced. At the beginning, everything is interpreted. Once it's run enough, 1,000 times by default on most JVMs, we say, okay, we're sick of running interpreted code that's slow. Let's actually do something about it. Ask a JIT compiler to give me a little better. That's the green stuff. But that's first step today is usually a profiling, low optimization compiler. But mostly it's trying to study what's going on in the code and adds more interesting ways to measure. And then when that's run enough, 5,000 times, 10,000 times around loops in most modern JVMs, we say, okay, this one really matters. Let's actually optimize it, throw everything we have at it. Let's get some of that really good blue code that's fast. And this is done independently for every single method. You could go through 7,000, 10,000, 20,000 methods evolving through this line. Eventually, all the code that is actually run enough times, 10,000 times around the loop, not that much, will be optimized, and we're running everything optimized. That's how we get to eventual speed. So this evolution is natural, and it reflects that ongoing conversation about thousands of things between a JVM and its JIT compiler. Now within this, there's some important things to note, and that is that JVMs today do speculative optimization, and speculative optimization is really a big part of the secret, it's not so secret, of why Java can be fast. And without it, there's not as much speed to get. So to give you a classic example of that, if we have code that looks like this, some class with some getter, that's meant to be extended. There are many types of animals in the world, dogs and cats and birds, but there's a color. And you know, we have a color field, and get color is how we get it. But we abstract it, we nicely encapsulate the field so nobody accesses the field, so we have a getter. But we want to be able to extend the class if somebody ever wants to define it differently. So this is good, clean, object-oriented code. But when we call getColor, we would really like to be able to optimize it to just go get that field. That's all this means. We want to inline the methods, see through all the code, throw away the calls, and do whatever other optimizations we can. If the method actually had more things we could do about it, we want to optimize those. And this is a valid optimization on a virtual call, as long as we know that in the known universe, only one implementer of getColor exists. So we can inline it. But if somebody loads a chameleon, and the chameleon redefines getColor to compute the color based on the tree it's sitting on, you have to throw this code away because it's no longer valid before a chameleon exists. So we can speculate to get the speed, and we have to be able to despeculate or de-optimize to recover from being wrong, right? And in fact, de-optimization is the thing that actually makes it possible to speculate to begin with and get the speed we get out of this stuff. What that means is when a JIT compiler delivers code, it doesn't just deliver code. It also delivers assumptions. Assumptions like, there is only one implementer of getColor, or this field is actually final, truly final. It hasn't been overwritten by anybody. Or, you know, something doesn't have a subclass, or maybe today is Tuesday. I've been running for 3 hours. They keep saying it's Tuesday, you know. Or things like, you know, assertions are off, or the language is English, you know, in this JVM. Nobody said it's English, but it is English, so we'll do that. And you know, I haven't seen strings or arrays above a certain size in certain places. We can go all the way to saying, the implementation of this method is exactly these bytes with this hash code, and therefore I could intrinsify the method, even though something. You could go that far. Now, by the way, not every one of these is an implemented optimization. I'm just throwing them at you as examples. More than half of them really are. So we take these assumptions and the code together, and that's what the JIT compiler gives the JVM. The JVM gets to install this code, but it also has to keep track of all these assumptions, and anytime any of them change, the code has to be thrown away, de-optimized, and go get another optimization from the JIT compiler. While that's going on, you're running interpreted code or less optimized code, waiting for the recovery from the optimization. So we get this shape, right? That shape translates to speed this way. We start slow because we're interpreted. We get faster and faster as more and more methods transition to the higher and higher optimizations, and eventually we stabilize. These ups and downs, that's the de-optimizations. We got super happy about one implementer, then somebody put a chameleon in the world. Well, I guess we have to throw that code away and re-optimize, right? So you get ups and downs. Now, the eventual speed that we have here and the warm-up that goes on the way is things I'm going to talk about addressing to some degrees. Let's start with the eventual speed. How do you make speed better? You JIT better. You throw more optimizations at things. You optimize harder. You compute better. You come up with cool new ways of doing things. And, you know, if you can make faster code fast, that's a good thing. And we have a lot of experience in that. We've been doing this for many years. And this is the part where I try not to brag too much about product, but this shows you the evolution of speed for our Zing JVM and the solution of speed for OpenJDK over the last 5 years. 4 years here. Sorry, I have an updated 5-year one too. So you throw a lot of thinking and optimization and hard work at it, and you can get the speed more and more and more, and there's more to squeeze. We can keep going. But better shading comes at a cost. Somebody actually has to do the work to crunch this and optimize it and think about it, and that's not free. And we can apply these optimizations, but we need the resources to do them. So we need CPU to crunch away at all these optimizations. We need memory footprint to hold the state and the graphs and all that, to compute all that. And in a powerful machine with 64 CPUs and many, many gigabytes of memory, this is a no-brainer. You could do this all day, it's fine. We could throw a lot of power at it. We have so much more power today than when JVM started that it's not even funny that we're thinking about optimizations and budgets of 1995. But what if you're in a constrained environment? What if you're running on a machine with only 4, 8, or 2, or 1 CPUs, a fraction of a CPU? At that point, you may not be able to afford the optimization or the memory. And you may just need to choose between optimizing or not. Like, there's a trade-off. Can I afford to do this? And the trade-off is not just one of space and capacity, it's one of time. So here's an actual example. This is a finagle-driven microservice running on a 2 vCPU container on regular OpenJDK style optimizations, actually regular OpenJDK. And you can see the behavior of throughput over time and CPU over time here. So we start off, we optimize, then we finish optimizing. So we threw some CPU at the problem. And the code got faster and then settled. So you could say that's just good enough, but you can do better. You can throw stronger optimizations at it. And that's what happens when you actually say, let's throw something more powerful at it. You get to 20% faster. But it took time, and it took CPU to get there on a measly little 2 vCPU container. It took 6 or 7 minutes until it was faster than the alternative. It took about 15 minutes before it settled on being faster than the alternative. And look at all the CPU we burnt getting there. If you're running for the next 7 days on this thing, that's certainly worth doing. However, if the first 15 minutes of behavior matter to you, maybe you can't do this. Maybe you can't afford to do this. So you lower your optimizations and get the red thing. OK, so that brings us to what can we do about this with a Cloud Native JVM? Well, I think it's obvious by now probably, but we could take this JIT compiler out of the JVM. You run it outside. It doesn't have to run on a 2 vCPU container. It can run as inside an elastic big Kubernetes application. It can have 3,000 CPUs for fun. And I'm not exaggerating, by the way. We have people deploying at that size, right? And then many JVMs could use the same thing to JIT for them, using the same logic, the same conversations, the same optimizations that they could have possibly done locally, but maybe could never afford to. We can actually start thinking of optimizations we wouldn't even do on a 64 CPU machine because that's too expensive. But if I've got a service that could do it all day, I could do that. So why would we do this? There are many reasons, similar to the why we do manage runtimes, but it all comes down to dollars. You can save money doing this in the cloud. Because when you take something like this, that looks like that when you do local independent optimization and make somebody else do it for you, you get the benefit without the cost. You get there faster, you get there without spending your CPU, and I'll take away the local one, and it's an easy choice. Which one do you want to run, right? Do you want to run what you can do on your own, or do you want help from the cloud, right? So you get help from the cloud, it's pretty quick, it's pretty easy. Now, there's a very valid question that comes up when you do this. Isn't this just shifting the cost? Am I not just cheating? And the answer is absolutely yes. Yeah, I'm cheating, right? All I did is shift all the work somewhere else, right? But the somewhere else we shifted to is a much more efficient place to do that work. Why is that? Well, to start with, the resources that we need to optimize, if they're only needed for a tiny fraction of the time, that beginning of the run until I get my 7,000 things done, and then I don't need them anymore. If I have them in my local V2 vCPU thing and they're crunching away, they're hurting my traffic, they're stealing my CPUs. For 15 minutes, I can't afford that, so I need more CPU if I want to do those things. But then I'm stuck with that CPU. I have to pay for it for the next day or two that I'm running. So a JVM needs to carry the resources with it, if it does it itself. But if you put it in a common service, then you get to share the capacity, right? We have many JVMs pointing to the same thing. It can compile for you and you and you and you and you, right? But more than that, it could be elastic. So when all of you are asking us for stuff, then we need capacity to do it. But when you start quieting down, we can shrink. And when you wake up again and do a deployment or autoscale, we'll grow. It's an elastic Kubernetes service in this example, and it could just fire up some spot instances to do more compiles, right? And then shut them down. This is a matter of minutes. I call this an aggressively autoscaling service because, well, it needs a lot of CPU some of the time. It needs close to nothing most of the time. And that's where the efficiency comes from. So elasticity is cool. Shared resource is cool. But wait, there's more. That's a Ginzu knife commercial thing. Here's some simple observations. For the vast majority of code we write, the code runs more than once, right? I know we run it once just to debug it. We find the bug and run it again with different code. But eventually, we run it more than once. It runs on more than one device, multiple instances. It tends to repeat the same thing and work on the same kind of problems with the same behaviors and the same profiles over and over and over again, even across instances of the run. And this is true not just for stable code like, I don't know, Cassandra. It's true for your microservice that you do rapid DevOps deployment on 5 times a day. Between your 5 deployments, it's running millions of times with these qualities, right? None of this is leveraged by existing runtimes. But if we have something that's being asked to do all the optimizations for all the instances, we can actually reuse the optimizations. We can even reuse speculative optimizations. So if we treat the code as code plus assumptions, and in this Cloud Native compiler, we cache the previous optimizations that we've done for that method, along with the 350 questions that were asked for that method, and the 350 right answers to get this code, then some of the JVMs will repeat that. And for those JVMs, we don't have to compute the optimization, we have the optimization. And when there are hundreds of them, there's a huge lift that comes from doing this. We're actually amortizing the cost of optimization across hundreds of instances rather than doing the entire optimization for one poor JVM on 2 CPUs times hundreds of times. Right? And what that means is we could say, okay, it's much cheaper to optimize, that's cool. Or we could say I can now afford to optimize like I've never been able to afford before because it's much cheaper. And you could go either way with that. So the work can be reused. So Cloud Native compilation is just better. Hopefully that's obvious. And the concept itself works. This is, when I started talking about this a few years ago, it was a concept. We ship a product that does this today. Okay? So we know it works. And it delivers all those good things, right? It improves all kinds of stuff. So that was part 1. Let's take the JIT compiler out of the JVM, make it a service, and now we have a Cloud Native JVM. Why? Because it's a JVM. It outsourced something to the cloud, and it contributes back. The fact that I compiled made it better for the next JVM because the cache gets full. Right? So it hits all 3 bullets. So let's talk about part 2. It fits very well with part 1. Part 2 is not about how to actually compute optimizations, but how to decide what to optimize and how. And that's about sharing experiences across JVMs and orchestrating how that sharing happens. So in this curve, let's look at the warm-up part of the curve, right? Now, the warm-up is not just about how quickly I can finish computing optimizations. It's actually about how quickly I decide to ask for them. I can have the fastest Cloud Native compiler on earth with the full cache, but this JVM would still wait until I did 10,000 slow things before it even asks for that optimization. With better JITting, we make things faster, but with optimization replays, we can actually avoid the learning. That warm-up is a learning curve. 7,000 different methods had to learn the hard way that they want to be optimized in certain ways. And they asked for something, and they got that something, and then hopefully that was it, but they elevated and maybe de-optimized, and eventually they figured out what stable is. And the neighbor did the same, and the neighbor did the same, and they're not talking to each other. Optimization replay basically relies on logging and replaying the decisions to optimize. So you record the optimizations done by one JVM. And you record the decisions as you go. Every time you ask for an optimization, every time you provide a profile for an optimization, you just record that you did that. You also record the dependencies for optimization. So if you were interrogated and asked for a static final value from some class that is not the class with the method, then you record that fact, but that means that that compilation is dependent on that class being initialized, because before it's initialized, we don't have that static final value, and we don't know what to constant propagate, and if we optimize too soon, we won't get the same quality of code. So anything that went into the answers that depends on initialization state of stuff, we record. That tells us for every method that was compiled, what the eventual compile after 5 deops was, and what it needs to wait for before that's okay to do. There are all kinds of tricks we could do beyond that, but we won't get into them. Now, basically, we're establishing an eventual steady state of sort of stable. We don't seem to be compiling more. What brought us here is the fact that we asked for these 9,000 things with these profiles. And that's how we got to where we are. On the other side, you feed that experience to a JVM when it starts. And the JVM primes itself with that experience rather than have to learn on its own. Now, it's still doing everything on its own organically for things that don't match this. But for anything that matches the dependencies that we recorded, when a method that somebody else optimized in a certain way reaches the point where all of its dependencies are met, you trigger a request to optimize. You tell your JIT compiler you want that to be better. This is not about the actual work of optimizing. It's about the decision to optimize, the triggering of the optimization, and the profile answers that you want to have ready when that optimization happens. So what this achieves is two things. The first one is it eliminates the de-optimization storm problems that often happen. In Java, lots of times we start, we might optimize code, but when we hit real traffic, we see a bunch of stuff de-optimized because some things are happening for the very first time when traffic hits. We can take that out because the recorded experience includes post-traffic behavior, so we know how to optimize without making the mistakes that need to be de-optimized, and only optimize with the assumptions that actually lasted. So that's one. But once we've cleaned that up, so we know what the final optimization needs to look like, we could do it before traffic starts. We can do it as soon as the code is loaded and initialized. We don't have to wait for traffic to happen. We don't have to wait for 1,000 or 10,000 things to run. We could just do it. Now, this on itself, on its own, that's just recording and replay of optimizations. We have a feature called Ready now in our JVMs. Doesn't have any cloud anything in it. But to do this with JVMs without any cloud interaction, you end up with some serious logistical questions, like where did you record the profile, and how did you get the profile to all those other instances? And what if the profile is 2 weeks old and you changed the code since then? And how do you even get it to them? Do you put it in there? Do you put it in your source control system, in your images, in your repo? The logistics get very interesting and harsh around this. We've had people using it with files for many years, but it was people who really, really wanted to, like traders. But if you use the Cloud Native approach, and instead of just saying it's a Cloud Native compiler, we call this an optimizer hub. It does both Cloud Native compilation and profile orchestration. You can actually make this just smooth and natural and simple. This is a concept talk about how this stuff works, but I have to transition to an actual example of what we do in our product. In the Azul Ready Now Orchestrator, which is the thing that orchestrates how we record and provide logs, you coordinate multiple instances and their profiles, and all you have to do is name your profile. Usually your profile is your application name and its version. In most cases, every time you rev your code, that's a new profile. You could theoretically share things across them, but the Ready Now Orchestrator basically takes over, and the first instances have nothing, and the next instances learn from the first instances. And usually the first instances are just canaries. You're just dipping your toe in the water, but they're gaining real experience. So by the time you get out of canary mode, you've got all the experience you need to get an instance up and running and able to handle traffic well. So more and more instances simply learn from what started. You now have a fleet of JVMs that is sharing experiences across it so that one JVM learning teaches everybody else what to do. We also do all kinds of nice cross-region coordinations across multiple regions in the world because people will use a canary only in one place, then carefully deploy in that place, but then they're happy and they'll just hit a button, on the East Coast after they did the West Coast, and they're not doing canaries there. So you need the profiles to get there somehow before you do this, and you can propagate them across instances and stuff in nice ways. So that together basically gives you something that both compiles the code and optimizes it well, remembers the optimizations in order to leverage them, and also tells JVMs that they should optimize in certain ways before they even see any traffic. The cool thing about these two things together is that they make each other better. Because when you tell everybody what they should optimize and what the profile that they should provide for the optimizer is, the optimizer sees the same thing happening from everybody because they're doing what they're told, not what they experience, which means they have a lot less noise, which means our cache locality and cache hit rates in precompiled things is much better. You can think of it, rather in terms of a JIT compiler, as an AOT compiler. The JIT I do for one JVMs is done ahead of time for the next JVMs and effectively prepared a whole bunch of precompiled methods for the next JVM that runs, assuming we have a good profile, assuming that everything repeats. It's usually not 100%, but it's a 95% hit rate on the cache, and the rest of the 5% will do what we normally organically do. So altogether, you get better speed because you've got something more powerful than you can ever afford on your own, and you get better warm-up and startup and other behaviors because something's coordinating experience across the entire fleet. And yes, this stuff is real. Like, we actually ship a product called an optimizer hub that does all this, and it's being used today in places where 10,000 JVMs across 100 different services are using a common optimizer hub to coordinate each of those application fleets and optimize for them. So it's a real thing. So that was part 1 and part 2. And you need to stay tuned for parts 3 and beyond, because we're still working on it. We're still figuring out which part is part 3 out of the 15 parts we might have. OK, so with that, wow, I'm surprised. I'm even 5 minutes early, and we have time for Q&A. So hopefully that worked for you guys. Hey. Thank you. I'm going to take some Q&A, but I saw the hand raised first over there. How much does it cost? I'm not a sales guy. A lot less than it saves. Okay. But I mean, that's usually how this works. At the end, it's all about dollars. You could just throw a lot of instances at stuff and, do other things. But yeah, I think the booths are closed now. But you can reach out, find Azul on the web, or reach out to me if you want. Be happy to talk later. Yeah.
Just curious, are the optimizations time-based? Like, does it have a concept of time throughout the day where it's like, oh, I need to be optimized this way at 8 o'clock because everyone's coming to work,
And then expire and do something else.
Yeah.
Theoretically, you can do that. We don't. I don't know of anybody who actually does that yet, but we definitely are considering that, given the vast amount of optimization power we can apply. So this is really what kind of speculations do we want to attempt and record, and that's why I threw in the today is Tuesday example, right? It's Tuesday all day, but at midnight that stops being true. So if there's a way to somehow record the fact that we relied on it being Tuesday and de-optimize at midnight, why not? I mean, if it's worthwhile. We don't do that today. It's an example of something to explore. We've had people ask about, something happens at 10 a.m. that changes stuff, but I'd like to be fast until then. And there are all kinds of questions like that. But right now, today, I'm not aware of something that has a time expired optimization in a JIT compiler. That's not to say you can't. That's, yeah.
Did you achieve that by using a different profile name during one part of the day or part of the day?
You would have to restart your JVMs. So if you knew that your afternoon work is different than your morning work, and you were willing to restart JVMs in a wave around noon and change the profile name accordingly, yes, you could do that. But I think you're asking about within the same instance without restarting, throwing it away. And then it becomes really, the JVM needs to decide to do this. So it's going to be an assumption that the time is good until the time is no longer good. Yeah.
So good. What if you have 9,000 JVMs running the same code base? Can they all submit different parts of methods optimize and then share the results?
So I'll answer that for the two different parts here. For the first part, the compiler, yeah, that's exactly what happens. Anybody can ask for any method to be optimized, and the thing will cache what it did. And if another one repeats that question and repeats the answers to the 350 questions that'll follow, then it's cached. What we do is for every method, we will cache a lot of variant compiles, because which compile you want depends on all those answers.
Does it preemptively share, or does it have to?
It manages a cache, right? So you get into cache management things like when do you evict, what's the capacity, and all that. And there's classic cache capacity management things for that. But we're talking about a persisted cache here. It's fronted by an in-memory cache for speed, but this lasts. It'll be there next week even if you restart everything. The learning doesn't go away. It gets pruned over time for things that aren't used for cache management. That's all. So LRU, or whatever you want to call it. Not really LRU, estimates. That's the compile caching. The other part is the profile logging, right? These are two separate things. The profile logging is the experience of different JVMs. Now, talking about this conceptually, you can actually merge the experience of many JVMs into one and decide to have a merged profile from 1,000 or 100 or 20 different instances where everybody teaches everybody something. One weird thing happened one place, you expect it to happen in another place, so tell them, right? You could. That's not what we do today. What we actually do today is listen to lots and lots of JVMs with the same profile. Within that fleet, pick a subset, 10, 20, to actually record, because what's the point in recording 1,000 different things doing the same thing? And within those, pick what we think is the best one, and that's what we'll tell others. So today, right now, all we tell a JVM is what one other JVM did. We just pick which one. Now, the orchestration includes all kinds of nice evolution things. For example, it turns out that if you record the profile and then give it to somebody, and they record their profile and give it to somebody, a few iterations actually makes this better. It might not be intuitive why, but I'll give you an example. When you decide to optimize things because somebody told you and not because you actually ran 10,000 things, you might optimize them earlier than before. When you optimize them earlier than before, you might then run into something that only happens once at the beginning of the program and didn't happen in the original case because it took 10,000 things before it got there and it was already some initialization or startup condition that only happens at the beginning. And when you do that, because of the reverse order, you'll end up de-optimizing this code that they told you because something at startup happened afterwards that the other one could assume never happens because it happened before. That situation loses an optimization for that method. But we then record the output of that situation, and then the next one has a good, clean one, so it learns what lasts and stuff. So they tend to clean each other up after a couple of iterations. Because of that, the orchestrator can play this game of saying, okay, I'll take your output, and when it's good enough, it meets this minimum criteria, I'll give it to others. And when our output is good enough, we'll give it to others, and so on. And usually you want to stop that after a few iterations. You can control this. There's a lot of controls in the orchestrator. Our experience is a 2-minute profile is much better than nothing. So you want that. But you don't want to have a 2-minute profile from the third wave replace an hour experience from somebody before that. You want to grow that minimum over time. But that's just, these are orchestration decisions you learn over actual experience. But fundamentally, we've found that taking the experience of one JVM and telling everybody to do that is good enough by far. We are always exploring more, and we're thinking about whether to merge things and whether to transform things and whether to even speculate inside these things and put all kinds of cool directives. There's lots we can do with the orchestrator. But that first step, that's a huge step. Everything else is just improving on it. Thank you.